All right. So, good evening, everyone. My name is Avik Mukhopadhyay, and I am one of the TAs for this course on digital signal processing. So, I welcome everyone to the week 7 sample problem solving session. And if you remember, in week 7, the contents that we covered included the inverse discrete time Fourier transform or IDTFT. Just a second. So as I was saying, in week 7 we discussed the IDTFT, inverse discrete time Fourier transform, and we saw the explicit formula for computing the IDTFT. Then we saw the response of LTI systems to inputs of the form A cos omega naught n plus phi, and then we also derived the discrete time Fourier transform for the sine function, and we also looked at the conditions on the poles of the Z transform for a stable system, both for a causal sequence and an anti-causal sequence. And finally, we also ended the discussion uh, with the response to suddenly applied inputs. So we just touched upon the concepts of zero input response ZIR and zero state response ZSR. So our sample problems for today will be centered around these concepts. So let's get started. Okay, I hope everyone can see question number 1 and 2 on the screen. So let's start with the first question. So in question number 1, we have been given 4 facts about a real signal x of n. Okay, we have been mentioned that the signal is real. The time domain sequence x of n is real, and it has a Fourier transform capital X of e power j omega, of course, and this real time domain sequence x of n satisfies these 4 conditions, given conditions. Okay, the first one says x of n is 0 for all n greater than 0. Second one says x of 0 is positive, and the third condition says the imaginary part of the Fourier transform is equal to sine omega minus sine 2 omega, and last one, which is the fourth one, it gives actually a value for this integral 1 by 2 pi integration from minus pi to pi mod square of capital X of e power j omega d omega equals 3. Okay, and given these 4 conditions and also the fact that x of n is real, we need to determine x of n. So that is our job. So you can pause the video and try to think yourself how to solve this, because there are certainly some hints given, and if you recall your lectures, then it might ring a bell. Okay, how to solve it. So try that. So the first thing which is given here is x of n is real. Okay, and if you, and also you can see in the third condition, the imaginary part of the Fourier transform of x of n is given. Okay, and so if you go back to your lectures, then in one of the lectures, while discussing the complex conjugation property of the Z transform, we saw that whenever the time domain sequence x of n is real, then the 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 Fourier transform capital X of e power j omega, it has, of course, it's a complex number, so it has two parts, a real part and an imaginary part. So whenever x of n is real, we saw that the real part of the Fourier transform is an even function, right? Just go back to your lectures and just verify it. And also, when x of n is real, the imaginary part of the Fourier transform is an odd function. Okay, and we have been given the imaginary part here of the Fourier transform and some conditions on x on n as well. So you see x of n is 0 for all positive values of n, that is for n equals to 1, 2 and so on, it is just 0. So if we just somehow know the values of x of n for all negative values and for n equals to 0, then we are done, that's it. So we know the entire sequence x of n. So even the information about half of x of n, half number of indices on the left hand side for negative values of n, and of course including n equals to 0, if that information is known to us, we are done. So, and as you know, any signal has two parts, an even part and an odd part. So for a signal x of n, the even part is x of n plus x of minus n whole divided by 2, and the odd part of x of n is given by x of n minus x of minus n whole divided by 2. So with all this discussion in mind, let's try to solve this problem. So I'll write it down. Let me just check if the recording is in progress. Yeah, it's fine. So, and we are in the call, right? Okay. All right. So let me first. So this is digital signal processing, and we are looking at sample problems from week 7 contents. Okay, and we are discussing the first question. So I'll just write it down for you. So the conditions that we are being given, the first one is x of n is real. Okay, and we also have x of n is 0 for n greater than 0. Okay, and x of 0 is some positive quantity. Okay, and we have the imaginary part of the Fourier transform of x of n. This is given as sine omega minus sine 2 omega. Okay, and finally we have also been given this condition. Okay, and our task is to find x of n. Okay, so by the way, this last condition here, 1 by 2 pi integration minus pi to pi mod square of cap x of e power j omega d omega, whenever you see such kind of an expression, this should remind you of something, right? Some theorem. So it should remind you of the popular Parseval's theorem, right? This is actually the expression for energy in the frequency domain. And by Parseval's theorem, we know that the energy in the time domain is equal to the energy in the frequency domain. So this essentially is actually your the energy in the time domain sequence. So basically summation n running from minus infinity to infinity, mod of xn, mod square of xn, that's it. So that's the energy of the time domain sequence. That is same as this quantity, which is 3. And why have we have been given this condition? Because like I was saying, so we don't know about the value of the sequence x of n at n equals to 0. Okay, so this condition will be, as you will see later, utilized in finding the value of x of 0. Okay, we just know that x of n is, x of 0 is something positive. Okay, we don't know its value. Anyways, so whenever you encounter such an expression, there is a possibility of an application of Parseval's theorem. So anyways, let's start solving this. So okay, okay, so just some known facts. Okay, you should already be familiar with all these things, but still I'm writing everything. Okay, so any signal or sequence x of n can be broken down into two parts. Okay, the even part here, ev of x of n is the even part of x of n, and this is the odd part of x of n. Okay, and what is the even part? It has this form. I already dictated it initially, but I am still writing it down because we might need this for solving the problem. And the odd part, it just has a minus sign. So if you just add these two even and odd parts, you get x of n, right? And now coming to our problem, so now I am coming to the solution. Okay, so okay, so we have been given that x of n is real. Just go back, see the first condition, x of n is real. So we know from our discussion during the complex conjugation property of Z transform, if you just recall the lectures, we know that for x of n being real valued, um, the real part of the Fourier transform is even function and the imaginary part of the Fourier transform is an odd function. So, but before that, let me just write it. So, the Fourier transform of x of n, which is x of e power j omega, it is a complex number in general, so it has two parts, a real part and an imaginary part. So real part plus j times the imaginary part. Oops. Correct? And now from our discussion, if you revisit your lectures while discussing the complex conjugation property of Z transform, we saw that for real x of n, the real part of the Fourier transform is an even function. So f of minus x is same as f of x whenever f is an even function. So I'm just writing that condition. Okay, this is an even function, and the imaginary part of the Fourier transform, it is an odd function, so we'll just have a minus sign, right? This is an odd function. Good. Okay, right. So now okay, so we have, I am writing it once again. The Fourier transform has two parts. Real part and imaginary part. Now if I simply just replace omega by minus omega, so we have e power minus j omega equals, and let me by the way label this first equation by 1, equation 1. And so by replacing omega by minus omega, what do we have? We have simply this, right? And now we know that the real part of the Fourier transform, it's an even function. So real part of x of e power minus j omega is the same as real part of x of e power j omega. Okay, we already saw this. And the imaginary part being an odd function, so the imaginary part of capital X of e power minus j omega, it's same as minus of imaginary part of capital X of e power j omega, right? So we'll just use that fact here. So what do we get? Okay, someone wants to join. Okay. All right, so I can see Venkat has joined. So just a quick confirmation if I am audible to you.
Yes, sir, you are audible, sir.
Okay, great. All right, so I was discussing the first question for today. So we are on the week 7 of this course. So these are some sample problems related to the contents of week 7. And remember, in week 7 we discussed the inverse discrete time Fourier transform, or IDTFT, and then we also derived the Fourier transform for the sine function, and then we saw the response of LTI systems to inputs of the form a cos omega naught n plus phi, and we discussed the conditions on the poles of the Z transform for stable systems, both for causal and anti-causal sequences. And finally, we ended the discussion uh, with a note on the response to suddenly applied inputs. Okay, so these problems are related to these concepts only. And in the first question, I was discussing, I'd already solved almost half of it. So in the first question, I hope you can see it. So we have been given 4 conditions for a time domain sequence x of n, and x of n is a real signal, it is already given, and it has a Fourier transform capital X of e power j omega, and the 4 conditions that are given are as follows. So in condition 1, you have the x of n equal to 0 for all positive values of n, that is for n equals to 1, 2, 3 and so on, it is 0, and the value of x of n at n equals to 0 is some positive value, we don't know. And the third condition says that the imaginary part of the Fourier transform of x of n is equal to sine omega minus sine 2 omega. And finally, the fourth point, it says that this integral 1 by 2 pi integration from minus pi to pi mod square of capital X of e power j omega d omega equals to 1, equals to 3, sorry. And given these four conditions, we need to determine the time domain sequence x of n. So, okay, great. So, uh, so any guess Venkat how to approach this kind of problem? So what's the first thought that comes to your mind given this information? We need to find x of n. We're discussing the first question. Yeah.
Yeah, I have now just log in now. I have not gone through the notes now. This is the time I'm attending.
I
Sorry, don't.
see. I see. I see. I see. I see. All right. No worries. You once we are finished with today's discussion, you can just revisit the lectures anytime, and then hopefully things would be clear to you. So, all right. So don't worry. So the thing is, yeah. So I've written down the conditions, given conditions here, and so actually, when we were discussing the complex conjugation property of the Z transform in one of the lectures, we saw that actually whenever the time domain sequence x of n is real, then uh, it is true that the real part of the Fourier transform, the real part of capital X of e power j omega is an even function, and the imaginary part of the Fourier transform is an odd function. This is true whenever the time domain sequence is real valued. All right. So, and since in this problem the imaginary part is given and x of n is given to be real, so there is a possibility of utilizing this consequence, right? So we will be using this result in this problem. And by the way, capital X of e power j omega is the Fourier transform of x of n. It is in general a complex number. That's why we are breaking it down into two parts: the real part and the imaginary part. The real part is an even function whenever x of n is real, and the imaginary part is an odd function whenever x of n is real. So, and also the first condition which was given, that x of n is 0 for all positive values of n. So essentially, we don't need to bother about the positive indices of n. So for n equals to 1, 2, 3, x of n is simply 0. And we don't know about the value of x of n at n equals to 0. We just know that x of 0 is positive. It is some positive value. All we need to find is the value of x of n for negative values of n, that is for n equals to minus 1, minus 2, minus 3 and so on. And of course we also need to find x of 0. So at the starting I have written some, by the way, can you see the screen? Can you see the solution?
Yeah, sir. It's
Great.
only that line alone, a real part plus imaginary part alone. I can see there.
Okay, okay, good, good. Yeah, yeah. So I'm, yeah, okay. And feel free to interrupt me, ask me anything which is not clear to you. So I guess,
Yes, yeah. If I have doubt, I'll just definitely call you.
yeah, yeah, yeah. I think it will be relatively tough for you because you haven't gone through the lectures, so it might be difficult for you at one glance. But anyways, I will try my best. So please ask any questions if you have. So So these are some known facts. I hope you already know it, or even if you don't know it, I have
Yeah,
written
sir,
it
I
down.
know about the even function and odd function, that formula and all I know, sir. No problem for me.
Okay, great, great. So now all I have done is I have written capital X of e power j omega as two parts, real part and imaginary part. And then what I have dictated to you just now, I have just written it down. The result that we got for x of n being real valued, this is a result. The real part is an even function.
The real part you considered as a cos theta, so you consider as an even function. Whether I'm correct, sir?
It's actually, yeah, you can think about it. You can think about it in that way, but it's actually, it comes from whenever we discuss the complex conjugation property of the Z transform, it follows directly from that. So if you just revisit that lecture, you can easily get. So I think it's from week 6, if I'm not wrong. So just recall those lectures from week 6, which are already uploaded on the website. So yeah, so yeah, but cos theta, that thing, it's okay, but while proving it, there is no need of this cos theta or sin theta thing in the proof. So anyways, so this is a known result, and I have written the first line again here into real part and imaginary part, and then what I have done is I have replaced omega by minus omega. So we have this thing, just omega getting replaced by minus omega. And now, since the real part of the Fourier transform is an even function, so real part of capital X of this thing, this term here, the real part of x of e power minus j omega, it's the same as real part of capital X of e power j omega because it's an even function. So I will use that. Okay. So we get this is the same as real part of x of e power j omega, and the imaginary part being a not function. So imaginary part of x of e power minus j omega is simply minus of imaginary part of x of e power j omega. So this is okay. And now let me label this by equation 2. Okay. So now if we just subtract equation 2 from equation 1, so if we just subtract equation 2 from equation 1, we yeah,
You will be getting 2 times of real part of x of e power j omega. Am I correct?
no, we are subtracting, we are not adding. So we will
Yeah, you are subtracting, no. So change the sign and add 2 times of j I am.
correct, only the imaginary part will prevail. Correct. So yes, so on subtracting equation 2 from equation 1, what we get is x of, on the left hand side we'll get something like this, okay, is equal to, so on the right hand side we basically get 2 times j imaginary part, so I'm bringing the 2 here on the left hand side, so it's the same thing, this, we get this, and now okay, now we know that the odd part of x of n is given by x of n minus x of minus n divided by 2, and if we take the Fourier transform of this signal, this odd part of x of n. So by property of linearity we know, yeah, go ahead.
Nothing, sir.
Okay, okay.
Yeah, we are going to replace that n by e power j omega. Where I'm correct, sir?
Yes, very good. So x of n goes to x of e power j omega, which is the Fourier transform of x of n, and then there is minus sign, and for x of minus n, this follows from the time reversal property of Fourier transform. This also goes to same but only with a negative sign. So all this has been discussed in previous weeks. So just I suggest you go through the lectures and it will be just clear. And the constant factor is just sits down here. That's it. So you see this term here is the same as this term. And now, okay, let me erase it. Okay, where is that? Oh, okay. All right. So this is same as j times imaginary part of this. Okay, right. Okay. So I'm writing it down once again. Odd part of we got odd part of x of n has a Fourier transform equal to j times imaginary part of this. And coming to the question, we have been given that if you look the third point here, the imaginary part of the Fourier transform has been given sine omega minus sine 2 omega. So we'll just replace this. So j times sine omega minus sine 2 omega. So, and now this is we know the formula for sine theta. It's e power j theta minus e power minus j theta by 2j. So if we use that formula, so we have this by 2j. And similarly for the second term we have e power 2j omega minus e power minus 2j omega by 2j. Okay. Right. So now this j gets cancelled. So we have, what do we have? So e power j omega minus e power minus j omega minus e power 2j omega plus e power minus 2j omega. Okay. And in general, actually, I'm not sure if you're familiar with the formula for the Fourier transform. So if we have a sequence like this, if we take the DTFT, Discrete-Time Fourier transform, we get this as summation in running from minus infinity to infinity x of n times e power minus j omega n. Okay, so this is just a formula for DTFT. And now, so we have the Fourier transform of odd part of x of n as this. So you see it also involves terms of the form e power minus j omega n, right? So in the first term, it's e power j omega times 1. So basically n is minus 1. So it represents the sample value x of minus 1, right? So if you take the all right, so this is in general actually. All right, so this part, this first term is corresponds to n equals to minus 1. Second term corresponds to n equals to 1, sample value at n equals to 1. Third term corresponds to n equals to minus 2, and this last term corresponds to n equals to 2. Okay, so actually x of n has only 4 samples. That's the takeaway. So it has this term corresponds to n equals to minus 1. This corresponds to n equals to 1. This term corresponds to n equals to minus 2, and this term corresponds to n equals to 2. So only 4 length sequence. X of n is only, sorry, the odd part. We are dealing with the odd part of x of n. So the odd part of x of n is a length 4 sequence, and it has samples only corresponding to these indices: n equals to minus 1, n equals to 1, n equals to minus 2, and n equals to 2. So this is basically, this is nothing but um, what can I say? So, and this coefficient here will be basically the value of the sequence at that time index. So what I can say is odd part of x of, for n equals to minus 1, right? So this times e power 0, and then we have plus odd part of x of 1 times e power minus 3 omega. Okay, similarly we have, it just comes from the formula of DTFT, x of minus 2 times e power 2j omega, and finally odd part of x of 2 times e power minus 2j omega. Right. So if we just, so where odd part of x of minus 1 is what? If you just compare from this to this, it's half. This is half, and at x equals to 1, this is minus half. This is minus half. And at x equals to minus 2, this is, so just compare coefficients of e power 2j omega, it is again minus half, and for x, for n equals to 2 we have half. Right. So okay, so at n equals to minus 1, it takes the value half. At n equals to 1, it takes the value minus half. At n equals to minus 2, it takes the value minus half, and at n equals to 2, it takes the value half. So I can actually replace this sequence in terms of, represent this sequence in terms of the shifted and scaled delta function, right? So I can write, okay, odd part of x of n as half times delta of n plus 1, because at n equals, this is at n equals to minus 1, this becomes 1, and times half, so this is the thing. And so this half factor is common actually, only the signs are just alternating. So for n equals to 1 I will have delta of n minus 1, and at n equals to 1 it takes minus half, so there will be a negative sign. Then I have n equals to minus 2, so delta of n plus 2, and what value it takes? It takes the value minus half, so negative sign. And we have n equals to 2, so we have delta of n minus 2. Okay, someone. All right, let me see if the recording, yeah, it's going on fine. And for n equals to 2 it takes the value half, so plus sign. Okay, right. So is this clear, Venkat, so far? Can you hear me? Hello?
Yeah, sir. Yeah, sir.
Okay. Okay, till now it's clear, right?
It's clear, sir.
Okay, great, great. Right. So we have found the expression for the odd part of x of n, but we need to find the expression for x of n in general. Now, okay, right. I'm going to the next page. I'm writing it again. So we got this delta of n plus 1 minus delta of n minus 1 minus delta of n plus 2 and plus delta of n minus 2. Great. And if we just plot this, it's always good to plot simple functions. So if I make a rough diagram of this odd part of x of n, okay, so we have samples only at minus 1, 1, minus 2 and 2. So if I label this as 0, 1, 0, 1, 2, 3, 4, let's say, and on the negative side we have minus 1, minus 2, minus 3, and it's minus 4. So at n equals to minus 1 we have half. Okay, so n equals to minus 1 we have half. Let's say this height is half. Okay, at n equals to 1 we have minus half, so it's just same height in the downward direction. Let this be minus half. And then we have at n equals to minus 2, it's again minus half. Oops. Something like this, it's again minus half. And finally at n equals to 2 we have plus half. Plus half. Okay, so of course this, as we expect, the odd part is an odd function, so it clearly is an odd function, as you can see, because it's just the flipped reflection about the origin, as you can see. F of x is f of minus x. So anyways, and for and we don't have any other samples, so it is simply 0 for this 3, 4, again 3, 4, and for 0 also. Okay, and it continues both sides. Okay, fine. So and so the odd part of x of n, you know that it's given by this, and we also know that x of n is 0 for n greater than 0. It's already given in the condition. So if you check the first condition, condition number 1, it's given. So this implies that x of minus n would be 0 for n less than 0. It's just the same thing. So this odd part of x of n would be x of n minus 0 by 2 when for n less than 0, because for n less than 0 x of minus n just vanishes. Okay, since writing it, since x of minus n is 0 for n less than 0. Okay, 0 is not clearly visible. Okay, so let's see. Okay, right. Or I can just change the sides and write x of n as 2 times odd part of x of n for n less than 0. And we already know, going back to the question, we already know the condition for n greater than 0. X of n is simply 0 for all positive values of n from condition 1. So we already know that x of n is 0 for n greater than 0. So all we need to find now is what about n equals to 0? That is not known to us. So we still don't know x of 0. That's the thing. We just know from the given information from condition 2 that x of 0 is some positive value. That's it. And since we already got that x of n is 2 times odd part of x of n for negative n, since we already got the graph for this, we can draw the graph for this for x of n for negative values of n at least. Okay, so let's do that. Okay, so let's say this is 0, 1, 2, 3, 4, this is minus 1, minus 4, and so on. Okay, great. So we just need to do 2 times odd of x of n for n negative. So at n equals to minus 1 we had half previously. So 2 times of half is simply 1. So at minus 1 we would have this height has 1. And for at n equals to minus 2 we had minus half. Twice of it is minus 1. It's just scaled by 2 times. So this will be minus 1. And that's it. For minus 3 onwards it's just 0. So 2 times 0 is again 0. We don't need to bother about that. Okay. But we don't know about x of 0. We still don't know. We still don't know about x of 0. And for positive values, x of n is simply 0. It is given in again. If you check condition 1, for positive indices it is 0. So we can directly put all them to be 0. And so on. Okay. Great. Now, so far we have exploited the first condition, second condition, third condition, and we have arrived at this point, and we only need to find the value of x of 0. If we know the value of x of 0, we are done. And the only thing we have not used is the fourth condition here. So the fourth condition is, so by the way, I'm not sure if you're familiar with this, but still, does anything come to your mind when you see this fourth condition here? 1 by 2 pi this integration equals 3.
It's a possible identity.
Exactly. Very good. Very good. Very good. That's exactly what I was expecting. So we just need to make use of the Parseval's theorem. That's it. And as you know, the result of Parseval's theorem, that the energy in the time domain equals the energy in the frequency domain. And this expression actually in the fourth point, it's the energy in the frequency domain basically. And it is given as 3. And it is the same as the energy in the time domain, which is summation in running from minus infinity to infinity mod square of x of n. That's it. Okay, exactly. So very good. So finally, from Parseval's theorem, we can say this is same as this. And this has been given as 3. Now we are just complete. So this problem is almost solved. So, so x of n has samples only at, you see, at n equals to 2, it has non-zero values. It has at n equals to minus 2, minus 1, and at 0. At 0, we don't know the value, but it's some positive value. That's all we know. It is non-zero at least. So we need to do this summation only for these 3 terms. So at n equals to minus 2, minus 1, and 0. So let's do that. So I'm going to the next page. So what do you get? You get this plus, actually for that, so what I mean to say is only the summation will be from minus 2 to 0, because they will only contribute to the non-zero terms. This is 3, and this implies this plus this plus this gives me 3. And going back to the graph of x of n, at minus 2 and minus 1, we have the values as minus 1 and 1 respectively. Squaring it gives the same, which is 1. So this is basically this plus this, and we still don't know about x of 0. So we get mod square of x of 0 as 1. So x of 0 can be plus 1 or minus 1. Now let's see the second condition. In second condition, it is clearly mentioned that x of 0 is positive. So there is only one possibility. So since x of 0 is positive, therefore x of 0 is 1, and that's it. So now we can simply complete our graph. Oops. So let's say 0, 1, 2, 3, 4, and so on. Here we have -1, -2, -3, -4, and so on. So we had this here as 1, at -2 we had -1, other terms we had 0, and now x of 0 we got finally as 1. This is also 1, and for positive when x of n is 0 we know. So this that's it. So this is x of n, and we can express x of n in terms of the scaled and shifted delta function as delta of n plus delta of n plus 1 and minus delta of n plus 2. So only 3 length sequence. Okay, that's it. So first question is complete. Okay. So now we are done with the first question. Let's move to the second question. Alright, so in the second question, we have been given again some 3 facts about
Excuse me, sir. What is given some of the fact in the question in the one, we have derived that x of n is equal to del of n. That's it. Whether I'm correct?
which one? Which one?
First problem, they
Correct.
given some of the fact for this. So we have derived that x of n is equal to del of n.
No, x of n is not equal to del of n. X of n is finally it comes out to be like this.
Okay, okay. Oh, depending upon the push, -1 and +1, it's going to change. Okay, I understood, sir.
Okay. So only the first condition which was given, it says only about the positive side of it. So
Okay,
it is 0 only for positive values of n.
okay. Second, according to second value, it says that above n value, they should take it as 0.
Yes, yes, just the first condition. X of n takes the value 0 for all positive indices, that is for n equals to 1, 2, 3, and so on. And the second condition says that at n equals to 0, it is some positive value.
Okay, I understood, sir. Thank you, thank you.
And like you said, from the Parseval's theorem, we just equated it, and then we found that x of 0 can be either plus minus 1. But since in condition 2 it is given that it is only strictly positive, so we chose x of 0 as plus 1. So, and then we just got this expression for x of n. Only it has only 3, basically it's a 3 length sequence, only corresponding to the indices n equals to 0, -1 and -2, there are non-zero values, and for all other indices it is simply 0. Okay, now for question 2. Okay, let's read the question. So we have an LTI system S, and it has an impulse response small h of n, and of course a frequency response capital H of e power j omega, and we have been given these 3 conditions. So whenever we apply this input in the first condition, if you see, if the input applied is 1/4 to the power n times u of n to the system, LTI system is, it takes it gives an output of the form g of n, where g of n is 0 for n greater than or equals to 2 and n less than 0. And so basically g of n is only non-zero for n equals to 0 and 1, right? And the second condition says that the frequency response evaluated at omega equals to pi by 2 is equal to 1, and of course, and this third condition says that h of e power j omega is same as h of e power j omega minus pi. So you can replace omega by omega minus pi. It gives the same frequency response. And given these conditions, we need to determine the impulse response h of n. Okay, so that's the thing. It's again it's an easy problem only. So let me write it down once again on the fresh page. It's good that you are interacting for today. So people don't often really interact in these live sessions, but these live sessions are meant to be
Actually,
interactive.
what happens, it is very difficult to attend the assignment question. Really, it's something which is very difficult to attend. Really, I go through the assignments and but I regular classes, but I
I
could
see.
not attend the class, the assignments. We are getting very poor marks. I don't know why.
Oh, I see. I see. I see. Okay. 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 But since actually, I think for so the upcoming assignment is, I think, assignment 7, right?
Yeah, tomorrow we have to, tomorrow, day after
Ah.
tomorrow I will submit the assignment.
The thing is, see, initially I had the plan of actually discussing the assignment problems itself, but since those assignments are meant to be graded, and that's why unfortunately I'm actually unable to discuss them. So rather, what I am doing is I am picking up some sample problems, so which are related to the concepts that were discussed in the class and solving them, so as to give all of you an idea. But yeah, had this not been graded and all those things, then I could have easily discussed it. Or if its deadline
No
had,
problem, no problem, sir. If I have any doubt over there, I will ask that question alone.
surely, and I think you might have I don't know if you have the email IDs of us, I'm not sure. If you have, you can mail me anytime. So I'm, anyway, let me write it down. Wait.
Definitely, just you share me, I will be definitely doing so.
I am just writing in the chat window. Wait. I'm sharing my email ID with you. You can, if you have any doubts or anything, you can just give me a mail. Okay. Yeah. So, yeah, you can just feel free to drop a mail to me. Once I'm free, I can just try to have a look at it. Okay.
Yeah, okay, sir. Thank you a lot.
Sure, sure, sure. No problem. Okay. So, yeah. So we were discussing the second question. Second question, yeah, it's an LTI system. Okay, so if we apply an input of this form to this LTI system, and it is denoted by S, and it has an impulse response h of n, it gives an output g of n. And as per the information, g of n is 0 for n greater than equals to 2 and for n less than 0. Okay. And let's say this is the input, so let me label this by some x of n. Okay. And we have been given some additional conditions, that is the frequency response at pi by 2 is 1, and it is also invariant if we shift omega by pi, which is this. It is also given. Now our task is to find the impulse response h of n. Okay. All right. So of course, since we are dealing with frequency response, so and we know in general the output in time domain of an LTI system is given by the convolution of the input and the impulse response. And by property, we know that that translates to simply multiplication in the time domain. So convolution in the time domain translates to multiplication in the frequency domain. Okay. So basically, what I'm saying is, so if the output is like this, so it's given by the convolution of the input and the impulse response, and in the frequency domain this goes to basically y of e power j omega equals, it's simply the product like this. So right, great. And here actually the output is denoted by small g, so I'll stick to the notation. I'll stick to the notation given in the question. So I'll use G. This will be capital G. Okay. Right. All right. So we have been given x of n. The input has been given 1/4 raised to the power n times e of n. So we can, and of course, product is a simple thing, right? Instead of convolution. For convolution, we need to take the sum and run over indices. It's tough, tedious job, it seems. Whereas in the frequency domain, it just boils down to multiplication. So that's a relatively easy task. So let's first find out the Fourier transform of the input x of n. So which is cap x of e power j omega. X of n is given. So let's do that. Let's do that. So x of e power j omega, we know the formula for DTFT. Times e power j omega n. And you can stop me at any point if you have any queries or any concerns, anything. And so what is x of n? X of n is, in the question it is given as this. Yeah. So can you help me with this?
Yeah, you can take the power as common, no, n.
Sure, sure, sure.
Then, since it is starting with u of n, we can start with n is equal to 0 to infinity.
Correct. Very good. Very good. So u of n becomes 1, and like you said, we can just pair the two terms together, and what we will get is this.
So we
So
can apply the formula 1 by 1 minus a, like that formula, where I'm correct?
exactly. That's the infinite GP series summation formula. Exactly. So that's what you were saying is, so S is a by 1 minus r. For infinite GP series with first term as A and a common ratio equal to R. That's the formula. So here the common ratio is actually, which is small r, it is actually 1/4 e power minus j omega. And the first term, if you put n equals to 0, we get a equals to 1. So if you do this, it's simply 1 by 1 minus 1/4 e power minus j omega. And here this applies only when this common ratio is less than 1, which is true here because mod of 1/4 e power j omega, it is actually 1/4 because mod of e power j theta is 1.
1.
Because yeah, correct.
1
So
of e power minus j omega is 1.
and this is satisfying this condition. So that's why it converges actually to a finite value. And so that's it. So this is the Fourier transform of x of n. Okay, great. So now, okay, I'm writing it again. X of e power j omega, it is 1 minus 1/4 e power minus j omega. And okay. Now we have two more things. So capital G of e power j omega and capital H of e power j omega. For g of n, for the output, we know just that g of n is 0 for n greater than or equals to 0 and n less than 0. And if we take the DTFT, this is simply, this is just minus infinity to infinity g of n times e power minus j omega n. But only actually if you see, this entire summation will ultimately contain only two terms because g of n is 0 for all these terms, for n greater than or equals to 2 and n less than 0. So g of n is only non-zero for n equals to 0 and n equals to 1. So this is nothing but only this, it's the same as this. Because for all other terms it will have no contribution. G of n will be 0. So
Actually, they are given that n is greater than or equal to 2, is it not? We should not take 2.
It is 0 for n greater than or equals to 2.
That's why I'm asking. They said for n is greater than or equal to 2, they said. Okay, okay. They said 0. Oh, g of n is 0. Okay, okay. I understood now.
As you see, right? So for 2, 3, 4 and so on, it vanishes. So yeah, and for n less than 0, it implies for n less than or equals to minus 1 basically. So yeah, okay. So and this ultimately gives us this. Okay, and now okay, okay, now our capital H of e power j omega, we can write it as this. Because we had expressed capital G of e power j omega as the product, so I can write capital H as capital G by capital X. So I've written it here, and we just got that capital G of e power j omega is small g of 0 plus small g of 1 times e power minus j omega. So this is small g of 0 plus small g of 1 times e power minus j omega. Now whole divided by capital X of e power j omega. And we just got that capital X of e power j omega is 1 by 1 minus 1/4 e power minus j omega. So if we divide it by that, so it basically 1 by this thing, it goes to the numerator and we have it in the product. So it's 1 by 4 times e power minus j omega. So this is actually product of this two. Okay, now I can expand this. Yeah, I hope I get something like this. I guess this is correct. So okay, let me go to the next page. So what I get is I can club these two terms for e power minus j omega, and the remaining term is this. Okay, and now so this is capital H of e power j omega, and we know that this has some form of like this, h of n times e power minus j omega n. So if we compare these two, so you can also write it as basically, so we have only three terms here corresponding to the indices n equals to 0, n equals to 1 and n equals to 2. That's it. So I can also write it as this times e power minus j omega plus h of 2 times e power minus 2j omega. And of course where h of 0 is simply, if you compare,
We can just compare h of 0 is equal to g of 0.
yes,
H of 1 is equal to g of 1 minus g of naught by 4.
correct,
Then h of 2 is equal to minus g of 1 by 4.
exactly, very good. Right. And so, and remember, we are trying to find h of n, the impulse response that has been asked in the question. So, so right now, so far we have actually seen that h of n has only three terms, right? So corresponding to the indices n equals to 0, 1 and 2. So therefore, what we can conclude so far is that h of n is a 3-point or 3-length sequence. So once if we are able to find these values h of 0, h of 1 and h of 2, we are done. We can find the general expression for h of n. So let's try to do that, and for that we actually need these given conditions. Condition 2. So condition 2 says that h of e power j pi by 2 is 1. So if we just put omega equals to pi by 2 here, so let me label this. Okay, let me label this by equation 1. This is nothing but, okay, we were actually calculating capital H, the frequency response. Okay, yeah, so this is, if we just label this by equation 1, and if we just put omega equals to pi by 2 here, what we get is, so the first term, so h of 0 stays at h of 0 on the right hand side, and then we have h of 1 times e power minus j omega. So h of 1 times e power minus j pi by 2, which is minus j. Okay, so
Actually, we
minus,
have to equate 1 is equal to h of 0 like that. Whether I'm correct, sir?
exactly. So I'm actually writing the right hand side first and then the left hand side. So I'm just,
Okay, sir.
that's the thing. So you're right. So actually, so yeah. So let's do that. So, and then we have h of 2 times e power minus 2j omega. So if you put omega equals to pi by 2,
Minus h of 2 will be there.
very good, yes, very good. And on the
Equal to 1.
equal to 1. Okay. So now what do we do?
Whether we can equate the real part and imaginary part?
Exactly. So I'm just writing in that form, and for one, you know that it's simply this. So like you said correctly, by equating real and imaginary parts on both sides,
From this, we can say h of 1 is equal to 0.
exactly,
Then h of 0 minus h of 2 is equal to 1.
exactly, exactly. This is 0 and h of 0 minus h of 2 is 1. So I can write h of 2 in terms of h of 0 as this. So yeah, okay. Now we are almost done. We just need to find any one of h of 0 or h of 2. And with this relation, we can find the remaining one as well. So now, um, so going back to, okay, where we started. Yeah, here. So now we know that this g of n here, small g of n, it's the convolution of the input and the impulse response. And the input has been given to be 1/4 to the power n u of n. So let's use that fact, okay, Let's use that fact, because ultimately we need to find this coefficients of this h of 0, h of 1 and h of 2. H of 1 we already got as 0. H of 1 we already got as 0 here. All we need to find now is h of 2 and h of 0. And you see that we have represented this h of 2 and h of 1 in terms of g, in terms of g of 1 and g of 0. So ultimately it's, if we know the values of g of 0 and g of 1, then we know the value of h of 0 and h of 2. That's it. So for that I am using the fact that g of n is given by the convolution of the input and the impulse response. Let's see if that helps. So now g of n is x of n convolved with h of n, and x of n is nothing but this, and so if we just use the formula for discrete time convolution, it is this, and what is x of k? X of k is, okay, I'll substitute the limit later. Let me first write x of k. X of n is 1/4 to the power n u of n.
We can make it as k is equal to 0 to infinity because we have u of n. Now itself we can change. No?
Exactly, exactly. So
Leave u of k.
then that will be 1. Okay. So since so this will be 1 basically. This equals to 1. So I can just remove that. Okay. And let me write this adjacent to it. Okay. Okay.
Now we can take the value 0 and 1 alone. It's whether I'm correct, sir. We can take 0 and 1 alone.
True, 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 true. So that exactly, that's what we will do. So we get, if we just expand from here, if we just further expand this summation from k 0 to infinity, it takes the form like this: h of n plus 1/4 h of n minus 1 plus 1/4 square h of n minus 2, and so on. Okay, and let me label this by equation 2. So now so remember, g of n was 0 for n greater than or equals to 2. So for n equals to 2 also it was 0. It is 0. So why this is g of n is 0 for n greater than or equal to 2, and for n less than 0. So putting n equals to 2 in equation 2, we get, so the left hand side becomes g of 2 which is 0, and on the right hand side we have h of 2 plus 1/4 h of 2 minus 1, which is 1, and we have 1/4 square h of 0. And if we continue like this, the next term will be 1/4 to the power 3 times h of n minus 3. And in that term, if we substitute n equals to 2, then we get 1/4 to the power 3 h of minus 1. But h of minus 1 is 0, right? Only these three coefficients are non-zero: h of 2, h of 1, and h of 0. But anyways, h of 1 is also 0, but that's it. We don't need to go beyond this, because otherwise if we just included the other term here also, like this, so it was like this, the next term, and putting n equals to 2 here would have given us 1/4 to the power 3 times h of minus 1. H of minus 1 is not in the picture, it is 0, so that doesn't matter, it has no contribution. So okay, great. Okay, so what do we get? We get 0 equals h of 2, and h of 1 we already got 0, plus this becomes 1 by 16 times h of 0. And now we can simply use the relation between h of 2 and h of 0. What did we get? This. We got h of 2 as h of 0 minus 1. We just utilize that relation here. So h of 2 was h of 0 minus 1. Why? Because since h of 2 is h of 0 minus 1. Okay. So what we get is or
So you will be getting 16 by 17 h of 0.
correct, correct, correct. Yes. So we got h of 0 as 16 by 17, and now we can easily get h of 2, because h of 2 is h of 0 minus 1. So just subtracting 1,
It will be then minus 1 by 16.
minus 1 by 17.
17, sorry, 17, sorry.
Good. So h of 2 is minus 1 by 17. Good. Okay. Now, so we have h of 0, h of 1, and h of 1 we already got 0. So we have h of 0 and h of 2, and h of 1 as 0. If we substitute these values here, so actually we even don't need to do that anyways. So these are the only non-zero values, right? So what we have is basically it's this h of n is nothing but, for 0 we have this 16 by 17, for 1 we have basically 0, and for 2 we have minus 1 by 17, and this is the origin. And for all other values we have basically 0. So 0, 0, 0. Similarly on the left hand side also, I should write it properly. Wait. and this is our origin, n equals to 0. So you're familiar with this notation, Venkat?
Yeah, sir, I know.
Great, great, great. So how can we write this in terms of the delta function? In terms of the scaled and shifted delta of n, how can we write it?
Then I can write it as 16 by 17 del of n.
Correct?
Then comma, that is plus or comma,
Hmm?
minus 1 by 17 del of n minus 2.
That's it.
That's
That's it.
it.
That's
Yeah.
it. These are the only non-zero values. So we are
Yeah.
done. Very good. So that's actually our h of n. Okay, let me. Good. So that's it. So we are done. We are done with the second question also. And okay, we have few more questions. So anyways, let's do it. I think this session is getting to be a long one. Anyways, so now coming to the third question. Okay, so the third question has given us a frequency response for the ideal high pass filter. Okay, so it takes this form: 1 for this set of values and 0 for the remaining values, and um, ultimately omega lies in the interval minus pi to pi in the discrete time case. So the interval has been broken down like that, and given this information about frequency response, we need to find a function g of n such that we can express the impulse function as sine omega c n by pi n times gn, such that this expression holds true. So basically, from the general approach is from the frequency response capital H of e power j omega. If we can take the inverse DTFT and find the impulse response h of n, we have the expression for h of n, and then we can basically find this g of n. We can equate it with this form and find g of n. That's the normal strategy. And then this is part A, and for part B, it has been asked that if omega c is increased, does the impulse response of the filter, which is h of n, gets more concentrated or less concentrated above the origin? That's the second part. So let's solve it part by part. So let's first deal with the part A. Okay. So let's
Actually, they given a transfer function. Okay, we will be taking inverse Fourier transform for that h of n. So we'll be
exactly.
getting sine omega n divided by pi n. I know that one. No problem for that.
I see. Yes, 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 yes,
Just
yes.
we'll be integrating 1 by 2 pi integral of that value. We'll be getting that one.
Exactly, exactly.
Okay, I know that one, sir. No problem for that. You need not to solve.
Yeah. Oh, okay, okay, okay. So yeah, this was in fact also discussed in the lectures also, but in the lectures there was a slight modification. So here the thing is, since here in the frequency response you have the value 1 for mod omega lying between pi minus omega c to pi, but in our lectures we had, if I am not wrong, this value was 1 from mod omega lying between omega c and pi, like this, if I remember. So in that problem you got something of that form, so delta of n minus this sine omega c n by pi n. So anyway, so let's do it. So basically our task is to find this g of n. So since you already know it, but I will still just write it, but I will just quickly go through it, okay, without wasting time to discuss each and every step. So good that you already know it. So let me just quickly write it just to make this document actually easier for everyone to understand later. So okay, okay. So we are discussing the third question, and we're looking at the part A. Okay, ideal high pass filter. So this is given. Okay, this is 0 otherwise. Okay. Now if you just
Actually, the question they said 0 modulus of less than or equal to minus just omega c. Just can you show the question, please?
sure. Yes.
Yeah, okay, sir. Okay.
Okay. So it's pi minus omega c actually. Yeah.
That is
So
that's it.
yeah. So if you just draw this, draw the frequency response. My drawing is horrible, but so just an approximate drawing. So basically, this is pi minus omega c to pi. Okay, this is 1 in this interval, and similarly, so this is omega by the way, and similarly on the negative side also. So we have minus pi plus omega c, and this is minus pi. So here also it is 1. This is 1. This value here, this height is 1, and this is the center at 0. This is how it looks approximately. Okay, great. So, and of course this is periodic, so it repeats after every 2 pi. So now all we need to do is we need to find, what do we need to find? First we need to find h of n, and then only we can determine g of n. So h of n, what we need to do is simply apply the IDTFT formula, so which is given by minus pi to pi capital E of this e power j omega n d omega, and so basically, so this h of this frequency response is non-zero only between these two intervals, right? From minus pi to minus pi plus omega c, and from pi minus omega c to pi. So let's do that. So do that. So here it becomes 1. So 1 times e power j omega and d omega, and similarly from pi minus omega c to pi, this. Okay, great. So the integration of e power j omega n becomes e power j omega n by j n, limits at this, and similarly for the second term we have this pi minus omega c. There's nothing really complicated in this, it's just simple mathematics. So Putting this, substituting this limits, we have this by j n e power j phi n by j n plus e power j phi n by minus e power j. Now it's clear. You can just pair the similar terms together. That's it, and you will obtain the form of the sine function. So I can take this in the denominator outside, and I can take this 2 factor here inside. So, and I am pairing the like terms together.
E power pi n, e power j pi n minus e power minus j pi n divided by 2j
Exactly.
minus of.
No, I am taking plus e power j omega c minus pi by, I'm actually writing this term here with the plus sign before. That's why I'm taking the plus sign. Minus minus e power minus j, this last term here, which is
C
omega
minus
c minus
minus
pi
pi of
n.
divided by 2j.
Exactly. Okay, and
So the answer
ultimately,
is 1 by sine n pi,
yes,
sine pi n
so, right.
plus sine omega c minus pi n.
Correct.
What I did know, while I'm solving, I have taken that minus of pi minus omega c, I have taken that one.
Yeah, it's fine. It's fine. It's fine. And
Then,
anyways, what about
whether
this?
it will disturb like that if I change the sign?
What exactly are you asking?
Actually, you have wrote there, no, sir. Sine of omega c minus pi of n, you wrote, no.
This term here?
There, what I did, I have kept that one in that upper limit values while you're substituting that, no, minus
Hmm.
of pi minus omega c itself, I kept that one.
Oh, that's
See,
fine. That's fine. That's fine.
yeah, okay, sir, you carry on. Let's check whether I'm getting the same answer for me
Sure,
also.
sure, sure, sure. So, and what about this first term sine pi n? It it is, remember, n is an integer. So what happens to sine pi n?
Now it will become 0.
Exactly, exactly. So ultimately what we are left with is, so this becomes 0, and I can use, for this second term I can use sine a minus b formula. So which is what?
Sine
Sine
A,
a,
sine A cos B
correct.
minus cos A sin B.
Good. If you do that, you get sine omega c n times cos pi n. So I'm just let's write it. Okay, just a second. So if you do that, you get sine omega c n cos minus pi n, and cos minus pi n is same as cos pi n minus cos omega c n. So let me write in bracket times sine minus pi n. Okay, no, sine pi n. Yeah, we'll get this, and this again, this sine pi n, this becomes 0. So the second term here basically it goes to 0, and we are left out with only this term.
I'm getting the same answer. What you just expanded? No, I took it as sine 180 minus theta. It's going to be again sine theta. No, that's the
Exactly,
formula.
exactly.
Yeah,
Anyway, it's fine.
yeah, I did like that. I got the answer as minus sine omega c n.
Okay, okay. Yeah, yeah,
You are
yeah.
correct. Don't erase it. It's correct. Nothing. Just I said my idea. That's all.
Yeah, I understand. I just used it for rough work. I will directly write the
Okay,
formula.
actually, it's just trigonometric. No, second coordinate.
Exactly, exactly,
We can
exactly.
use it. That one we can solve it easily.
Exactly. So what we got is sine. There's nothing complicated in this. It's just any way you do it, it's fine. This. So I'm going to the next page. So you get sine omega c n by pi n, so whole thing, multiplied by cos pi n. And I can write
G of n is equal to cos pi n.
exactly, exactly. And I can also, in fact, write it in a different form. So cos pi n is basically minus 1 to the power.
Minus 1 par n.
Hmm. So it alternates for every value of n. It just alternates the sign. It takes value 1 for even indices and minus 1 for odd indices. It's just the same thing. So that's it. So this is actually is in the desired form. So you see sine omega c n by pi n times g of n. So this is, if we compare with sine omega c n by pi n times g of n. So we have, therefore g of n is basically our cos pi n, which is also minus 1 to the power n. Okay. So we are done with part A. Now in part B, it has been asked if omega c is increased, then what happens to this h of n, the impulse response of the filter? Does it get more concentrated or less concentrated above the origin? So ultimately, you see this. This is h of n. So this. So, so h of n is what? H of n is the sine function times minus 1 to the power n. This is h of n. So this, if you ignore this minus 1 to the power n, this first term, it's like a sinc function, right? In general, the sinc function is of the form some sine pi n by pi n. This is the sinc.
We will be applying a hospital rule for this.
Yeah, you can
Okay.
apply a hospital rule, but I just need, in general,
We will be getting rectangular form.
yeah, but we don't need to take any Fourier transform or anything. We just need to observe the pattern. As omega c increases, what happens to the, I mean, the oscillations around the origin? Do they get more compressed, more concentrated, or less concentrated? So obviously, so we will see that. Let's see. So in general, this um, this sinc function, if you see, sin pi n by pi n, if you say, it has formed something like this. It's not a good picture, but it's roughly like this. And this amplitude is 1, and it's plotted against n. plotted against n, and okay. So, and of course this I have drawn as a continuous function, but in our discrete time we will have basically some samples of this, right? Like this. Let me use the red color only, or maybe green color. So like this. So this is one sample. 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 Like this. Like this. So yeah, because n takes only like integral values. So so you see, so and so this in our expression of h of n, we have a similar function like a sinc function only. It's just if we can just do, we can write this as sine omega c by omega c n times basically omega c by pi. That's it. This factor we have to take as an adjusting factor. That's it. So this term is in the form of a sinc function. It has a similar plot like this. So anyways, so what I want to say is, so and we also have a factor of minus 1 to the power n multiplied. So basically we will have the form of same as of sinc function, but due to this minus 1 to the power n factor, at every consecutive sample we will have a flipped sign basically. So for even values of n we will have positive amplitudes, and for odd values of n we will have negative amplitudes. That's it. So it's like this, approximately like this. Wait, um, this. So at 0 we have some value here, and this value actually is, I expect it will be pi omega c by pi, because what you are doing is, it's basically the, like you were saying, limit n tends to 0 h of n. So limit n tends to 0 sine omega c n by pi n, and minus 1 to the power n is just 1. So this you can write it as sine omega c n by omega c n times omega c by pi. So this is 1 times omega c by pi, which is omega c by pi. That's the amplitude at n equals to 0. So this is for n equals to 0. Now for the sinc function we expect something like this, and then it comes to 0 eventually, and it goes like this and this and this. It decays gradually like this. But due to this minus 1 to the power n, we will have alternating signs. So for n equals to 1, we'll have like this. The amplitude will be negative. And then for the next term, we will have again positive sign. And then eventually it will come to 0 at some point. Okay. And what will be that point? That will be basically pi by omega c, because we have sine of omega c n right in the numerator. So at n equals to pi by omega c, it vanishes. It first becomes 0 at this point, and similarly it goes on like this. On the other side also we have a similar pattern like this. And again it comes to 0 here also. It will be completely symmetrical. Okay, and it goes on like this. So the takeaway is that, so you see it becomes 0 at n equals to pi by omega c. Now, if in the question is it is asked what happens if omega c is increased. If omega c is increased, this point becomes more and more close to 0. This value becomes less, pi by omega c. So, so these the impulse response, these oscillations basically, they become more and more concentrated about the origin, right, as omega c increases, because this point shifts towards the origin. So we have more rapid fluctuations like this about the origin, like this, more rapid as omega c increases. Okay, so that's the thing. So the whole point of drawing all these graphs was just to illustrate that. So the thing is, as omega c increases, the significant, I'm talking about the significant central lobe, the main lobe, significant central lobe of h of n becomes more concentrated. Around the origin. That's it. So is it clear, Venkat?
Sir, I can understand. Am I over there?
Okay, great. So, okay. So we are done with the question number 3, I guess. Okay. So this was part B, right? Did I? Okay. So this is starting of part B. Okay. Okay. Now going to question number 4.
Sir, if you don't mind, let me solve and bring by tomorrow. Whether we'll be handling tomorrow the class?
Unfortunately, no, because my slots are every Monday, 6 to 8 p.m. So
Ah,
there are two other TAs actually, and as far as I know, there is one more session tomorrow from 6 to 8
8.
p.m. That is every Tuesday. So there will be another TA. So his name is Sai Dinesh. So I hope he might
Yeah,
take the
I'm
class.
attending the class from the last week because I feel very difficult to trace out the question. That's all. Okay,
I
I
see.
can
Okay.
solve this one. No problem for me.
Okay, so fourth one you can directly use the convolution also, but the idea here is in our week 7 lectures, sir has discussed the response of LTI systems to inputs of the form a times cos omega naught n plus phi. So you can directly, given the frequency response, the magnitude and the phase, you can directly write the output. So here also, if you see, the input is of that form, 5
Any
times.
whether we can convert, we are going to do DFT for
Yes.
X of n and H of n also DFT. I have to take it.
Hmm.
For cos omega, I can take it as e power j omega plus e power minus j omega by 2. That formula I can use and get it. It will be easy, I hope so.
Yes, yes. Yes, that's how I actually the outputs are obtained. But uh, as you will see, so I'm not solving it. I'm writing. Um, this has already been derived in the week 7 content. So if you give an input of the form a cos So what you told was exactly the right way. Omega naught n plus phi, if you give this input to an LTI system with frequency response h of e power j omega, and you can write h of e power j omega as magnitude times some phase factor. So let's write it like mod h of e power j omega, which is the magnitude, times e power j times the phase. So this is the angle of the frequency response. So angle like this. Then in the output you will get, it will be of the similar form only as the input, just it will undergo two things. There will be a amplitude scaling, the amplitude will be scaled by some factor, and the phase will be shifted by some factor. So the expression that you will get is, it will be, the amplitude will be scaled by a factor of the magnitude evaluated at the given frequency, which is omega naught. So capital H of e power j omega naught, this thing times your actual input, which is a cos omega naught plus phi, plus there will be one phase shift, and that shift will be by an amount of the phase response evaluated at, again, the given frequency, input frequency. That's it. So you see two things. This is the amplitude scaling, and this is the phase shifting. So this is a known result, okay, and this actually comes from that way only. You express cos in terms of e power j plus e power minus j by 2, and then you ultimately get the output corresponding to the individual parts and then add them together. So here in the question, if you go to the question, it's just the same. It's 5 cos omega by 2, sorry, pi by 2 n. So 5 cos pi by 2 n. So here our, if you compare with a cos omega naught n plus phi, a is 5, omega naught is pi by 2, and phi is 0. And you already know the impulse response. Impulse response is half raised to the power n u of n. Okay, I am not solving it completely. It's always good, like you said, to yourself. So it was what? It was this. So you first find h of e power j omega. Then find its magnitude, and also the phase.
Actually, we will be getting that h of e power j omega is nothing but 1 divided by 1 minus 1 by 2 e power j omega. From that, we have to
Exactly,
make,
exactly.
we have to take the modulus of that one. Huh?
Exactly. You have to take the magnitude to take the mod and also find its phase. And then you just need to evaluate it at the given frequency, which is pi by 2, to obtain the output. Okay?
Okay, sir. Okay.
So that's the way. Actually, otherwise, what you could have done is just done the convolution, because, but convolution sometimes, it becomes a lengthy task, because here we have two infinite duration sequences. Then convolution, doing convolution, no. Rather, this is an alternative process using the frequency response of LTI systems. As a good exercise, you can also first solve using this frequency response approach, and then also separately do the convolution and actually verify the answer if they are correct or not. So, so uh, so I'm just I will just write you the answer. Okay, so just check, just verify whether you get this or not. The output, I found the output to be something like this. Approximately. So you can check if you also get this or not. I hope, yeah, this is, yeah, yeah. So you just check this. Should be easy enough. And finally, these are the two questions that are remaining. These are also very straightforward questions. So fifth question. Any doubts in these last two questions, Venkat?
Actually, no problem, sir. It's just they given to find the input, determine the input sample response. Okay. That is, we should consider the x of n is equal to u of n. Where I'm correct?
No, unit sample response, it's the same as the impulse response basically.
We have to find h of n. Where I'm correct?
Yes, h of n.
Okay, it's okay. Then okay, I have to get x of says y of e power j omega divided by x of e power j omega. I will be getting h of omega. Correct, correct.
Just a second, I think someone wants to join. Oh, already we have almost concluded the
Ending
session.
session.
Haha.
Okay.
So, but anyways, yeah, that's one way, of course. And also, what you can do is you can also take the Z transform also. So you can
That will
find
be easy. Z transform. We take a inverse Z transform. We will be getting. We can apply partial fraction. We will be getting
exactly,
it.
exactly. So these methods have already been discussed. So you just that's how I also work it out. So you can take the Z transform and then find h of z by dividing y of z by x of z. Then do partial fractions. Then actually use some results because in the fifth question, see, it has been given that the system is stable, and whenever the system is stable, that implies that the impulse response, which is h of n, it is absolutely summable, right? It's
Yeah.
summation, that's the condition, summation from n running from minus infinity to infinity mod of h is.
Whether the system get inside the pole and outside the pole, the system will stable, sir.
That is one condition that is actually used in the sixth question. So what you are saying is, uh, for a causal sequence, the poles of the Z transform should lie inside the unit circle, and for it to be stable, and for an anti-causal sequence, the poles should lie outside the unit circle for it to be stable. Okay, and so that's it. So but here in this fifth question you don't actually need such concepts. You so once you figure out h of z, you know the pole locations. Okay, um, wait wait in question number 5, again verify. This is what I got. Okay, plus 3 by 8 times 1 minus 3 z inverse. Verify if you get the same thing or not. And now, what about the pole locations? So, pole locations are at z equals to 1/3 and z equals to 3. And as you know, the ROCs are bounded by the poles, and depending on these two pole locations, there are three possible ROCs. So what are the possible ROCs? Stop me if any step is not clear to you. So we have z equals to 1/3, which is the smaller value, and z equals to 3 is the larger value. So one possibility is it is lower than even the lowest value. So mod z is less than 1 by 3. Another possibility is it is greater than 1/3 but less than 3. That is, it's an annular region. And the third possibility is mod z is greater than 3. These are three possible ROCs. And now in our question it is given that system is stable. Okay, and this stable, this keyword, this automatically implies that our impulse response belongs to the class of absolutely summable sequences. So this is actually finite. Okay, and in words you can write h of n must be absolutely summable. In continuous time case, it is absolutely integrable. Here in discrete time case, it is absolutely summable. And now, if you go revisit your lectures, whenever this is the thing, whenever the h of n, the time domain sequence is absolutely summable, then the unit circle e power j omega or whatever mod z equals to 1, that unit circle should be the part of the region of convergence or ROC. So it has also been discussed in I think week 5 or week 6 lectures. Okay, this implies that the unit circle mod z equals to 1 belongs to the ROC. Absolute summability implies the unit circle is a part of the ROC. Now given these possible choices for ROC, what is the correct choice given that unit circle is part of the ROC? Out of these three possibilities, we know that mod z equals to 1 belongs to the ROC. Out of these three, yes, Venkat?
Sir, whether we can take a second condition?
Exactly. So this one, this includes mod z equals to 1, the unit circle. So this is our correct choice of ROC. So you take ROC as this, and then find h of n. H of z, you already know this. This also you need to verify it. Then find h of n. So actually you will observe that this h of n, it will have two parts. One will be a causal part and another will be an anti-causal part. And while discussion of the inverse Z transform, so you know that whenever we have functions of the form like this 1 by 1 minus a z inverse, if it's causal with this ROC, it has an inverse Z transform which is of the form a power n u of n, whenever the ROC is outside of a circle. And for the same thing, if it's of the form, if the ROC is inside of a circle, then the time domain sequence is of the form minus a power n, minus n minus 1. So use this. So use this. Use these relations. Why is it not okay? Okay, there's a lag. Use these relations. This might be useful. So yeah, because this ROC actually involves two parts, right? It's an annular region. So for one signal, you have to consider mod z greater than 1/3, and for the other component, you have to consider mod z less than 3. So you'll have in the time domain sequence in the impulse response, you will have two terms, one of the form a power n u of n, the causal part, and another one of the form minus a power n u of minus n minus 1, which is the anti-causal one. So just solve that, find h of n, okay, and again verify that you get h of n as minus 3 by 8 times 1/3 to the power n.
N u of n
Yes,
plus
and
3 by 8. Oh, so it's minus 3 by 8. Power 1 minus sorry 3 power n
yes,
u of minus n minus 1.
very good, very good, exactly. So that's it. So that's it, and just so that's also the fifth question is done, and for the sixth and final question, so you already know this concept. This was discussed in the last week 7. So here it is mentioned that the z transform is given, the transfer function h of z is given for stable LTI systems, and without using any inverse z transform, we need to, so in the previous question we did use the inverse z transform, but here without using inverse z transform, we need to determine whether each of the following is a causal system or not. So okay, so the okay, so the remark, the main concept here is that for a causal system to be stable, all the poles of the transfer function should lie inside the unit circle, strictly inside the unit circle. And for an anti-causal sequence to be stable, all the poles should lie strictly outside the unit circle. So just I'm writing it for a causal and stable system, all the poles must lie inside the unit circle. And you can obviously guess the one for anti-causal and stable system, it should be outside the unit circle. So let me just discuss only one part A. Okay, in part A, if you see, I'm writing out the transfer function here. So h of z is given as this. Okay, now just use this result and can you determine if this is a causal system or not? First, you need to check the pole locations. Tell me the pole locations. for this.
One is z is equal to 0.
Is it z equals to 0? Pole locations.
Oh, it's the inverse of
Exactly, exactly.
infinity.
Ah, okay. So pole
Second one
location.
is z is equal to 2.
Just a second. So first is z equals to infinity.
Second
Uh,
one is z is equal to 2.
is it z equals to 2 or z equals to half?
1 by 2 1 by 2
Yeah,
and 1 by 3.
correct. So now see what we have written in the first two lines and now conclude whether it's a causal system or not. We have found the pole locations. For a causal and stable system, we need the poles, all the poles to lie strictly inside the unit circle.
We have to take only one two poles.
No, but you see this
It has infinity, in that function.
exactly. So that's not lying inside a unit circle. Wait, where is my? Okay, this 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 is the culprit. So there is a pole sitting at infinity. So which is not inside the unit circle. So we can't. That forbids us from the system to be causal. So there is a pole at infinity. Therefore, system is not causal. Okay. If this z inverse term was not there in the expression of h of z, then it's fine. Then the system would have been causal
Actually,
because
we can conclude like itself without solving the problem.
yeah
They are
we
saying that system is stable in that question.
yes yes
That's why we need not to solve that when we can conclude like this itself. The system is not causal.
yeah this you have to do this way only because you just look at the expression of h of z and just check if the poles are lying inside the unit circle or not because it has been given that it is a stable system and all you need to check is whether it is in addition to being stable it is causal or not and we know the fact that for stable system to be causal for both these conditions, that is causality and stability, all the poles of h of z should lie strictly inside the unit circle. That's all you need to check. Okay? So that's what we have done. We don't need to find any inverse z transform or anything. Just check the pole locations. So similarly, you just do for B and C. It's also very straightforward. Just check the roots of the denominator, that is the poles, pole locations. Okay. Any queries? Any doubts?
Yeah, no, sir, no, sir. I will try that questions.
Okay, sure. This is just straightforward. It's similarly okay. Similarly, solve for 6b and 6c. So I am verify. Okay, for 6b. Okay, yeah, did I solve it? Okay. So for 6b, verify that it is actually causal, and for 6c also verify that it is not causal. Okay.
Actually, for second roots, it's coming 1 by 4 and 3 by 4. Z is equal to 1 by 4 and Z is equal to 3 by 4. It's coming roots.
Z equals to minus 3 by 4, right?
Yeah,
1 by
minus 3
4
by 4
and
and minus
so obviously both are inside the unit circle.
unit circle. So they are causal.
Exactly. They are already stable and they are both stable and causal. Okay.
Causal. Okay, yeah.
Very good. So you have already solved 6b, and similarly, same method follows for 6c also. Okay. So we have worked out all the problems, and thanks to you that you have helped me at every step. And so yeah, and like I said, feel free to drop any mail to me. So I hope you have got it, right? I have written it in the chat box. Okay, can you see it?
Sir, I note down
Okay,
the mail.
okay, 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 great, great,
Thank
great.
you, Latli. Really, very live section today I had.
Oh yeah, yeah. It was good for me also, because actually we are supposed to have this session as an interactive one, but unfortunately we don't get much people in the audience like you who are actually interacting. So, but yeah, I was also lucky
Yeah, I'm
today.
working as a assistant. I'm working as associate.
I
Uh,
see, I see, I see, I see.
yeah, I interested in doing courses. That's why I'm just taken this one.
Okay, okay, okay. We can stop the recording now, right?
Yeah, okay. Thank you.